All right, so here in this module, we're going to continue talking about binary eutectic phase diagrams. All right, so we've went over compositional ranges here on the left side of this lead tin diagram from less than 2%, from 2% to this 18.3%. Now we're going to sort of skip over and we're going to look at exactly compositions that are exactly the eutectic composition, so CE, which is right here. So we're looking, in this particular case, it's 61.9 for this lead tin phase diagram. And so this is the eutectic microstructure, and here's a picture of it, and we're going to kind of talk about how this results. But let's kind of go through it first. So if we're kind of looking at the cooling of this alloy, right, we're going to start with liquid. The liquid is uniform. And then what we see is that this reaction happens right at that eutectic temperature, right, of, in this case, 183 degrees Celsius. And so at that temperature, it's a very specific temperature, which is why we talk about the eutectic reaction. We go from liquid to that two-phase mixture. And you see here a very distinctive structure, this sort of striped pattern, and you see it over here as well. So you can tell that there's a mixture of phases, right? Because there's light regions and dark regions. That's the alpha and the beta. And we call this the eutectic microstructure. And specifically, the structure here is the lamellar structure. And you can think of it as laminar, the sheet-like structure. So that's why we call it laminar. And each of the layers is a lamella, and it's alpha and beta. So they're alternating layers of alpha and beta. So that's what we see here. And we can determine the amounts of those phases by using the tie line underneath those amounts. And so we can use the tie line just like we have before to determine the amounts of alpha and beta that we would have present in this microstructure. But let's look a little bit more about how this particular shape arises. So we know that alpha and beta have to simultaneously form at this very specific temperature from the liquid. So here's kind of the growth that happens. So we have a liquid out front, and the reason we have this shape and this growth pattern is because the liquid, if we look at this, has a composition of 61.9, yet alpha and beta are very lead and tin rich. So basically, the lead and tin in the liquid need to diffuse from these respective places. So the alpha here, if we go back, alpha here, this is basically pure lead, or close to pure lead, right? So any tin in the liquid around that will have to diffuse to beta, and any lead in front of the beta, which is tin rich, will have to go to the alpha phase. So basically there needs to be atomic diffusion to redistribute the lead and tin in front of these. And this is the easiest way to do it, to have these thin layers where the tin can diffuse over here and the lead can diffuse here. That's kind of the easiest way to ensure sort of short diffusion distances out front of the liquid. And so that's kind of why this particular microstructure develops because of the diffusion required for this kind of redistribution of particles out front. All right, so that's what occurs right at the eutectic. But to the left and to the right of those compositions, we have other regions, right, of compositions. And those are known as hypoeutectic, if we're talking about to the left of the eutectic here. And then we have hypereutectic, which is to the right of the eutectic. So hypo, hyper. So those are the two regions that we see here. And if we sort of skip ahead to what these look like, is you'll see that there's actually still the eutectic microstructure, that lamellar structure, and then in both of these. So you see it over here, you see it over here. But we do have other particles not part of that eutectic microstructure. And so in this case, in the hypoeutectic side, it's closer to alpha, and we see alpha. So we have this region of liquid plus alpha here, and alpha's over here. So this is going to give us alpha. On this side, we have liquid plus beta, and so we're going to get beta along with the eutectic microstructure. So I do want to go over a little bit of a naming convention that's often used when we talk about these distinct regions. And that's what we call a microconstituent. And all a microconstituent is, if you think about this word, is micro. So we're talking about visible on the micro scale. So think of optical microscopy. And a constituent is something that's sort of identifiable and characteristic. So this eutectic has a very distinct layered structure. So even though it's a mixture of phases, we like to think of this as a eutectic microconstituent because it's, kind of unique. So it's composed of 2 phases. So don't, nothing changed about the number of phases here. It's still 2 phases, but it has a distinct look to it, right? So we call this the microconstituent. Same thing here. This could also, the particles of alpha are also, clearly identifiable characteristics. So this could be another microconstituent. So it's just a name to give something that's distinct on the microstructure. So this is for hypo. The other part of it is we call these primary, and that's because they form above the eutectic structure that you see here. So we call these primary alpha, and we call these ones primary beta, and we'll get to that in a second. All right, so now let's look at that hypoeutectic region. So we're below the CE, so we're in this region here. So we're at about 40, anywhere in here, but we're using 40 as an example here. So this is hypoeutectic. And if we start, we get 100% liquid up here, as always. And the first interesting thing is going to happen here when it crosses this liquidus. And we're going to start to form alpha, because that's what's in this region. And so we have liquid plus alpha, so alpha particles. And then at the end here, we'll start to form, or we'll basically form more and more alpha at this point. And when we do that, we know that the compositions of the liquid and alpha change, right? So if we do a tie line at any point, the ends are the compositions, right? So it starts up here. This is the composition of alpha, and then it goes down here, and this is the final composition of alpha. And the liquid starts here and has a final composition here. So what you notice is that the liquid composition, as it cools, has to follow the liquidus until it gets down to this point. So basically, we keep forming alpha and alpha, more and more alpha, as we go down in temperature in this region, until the liquid has the composition of the eutectic. We stop forming alpha, and at that point, we form the rest of it. At the liquid with that composition forms into the eutectic mixture of alpha plus beta. So that's why we say that this alpha forms up here is primary, because it forms first, and we can determine the amount of alpha, primary alpha, that forms by doing the tie line above the eutectic temperature. And then below, we can use the tie line to determine the total amount of alpha and beta in the system, because some of it will be primary and some of it will be eutectic. All right, so this is basically kind of talking about the same thing we just talked about. So below the liquidus and above TE, we're forming alpha, and then the composition of the liquid increases. And like I said, just above the eutectic, we can determine the amount of alpha, or the compositions of alpha and liquid, and therefore we can determine the weight fraction of alpha and liquid. And in this case, they're basically the same. So it's 50-50. You can kind of see the links are equal. So that means that we have 50% that's primary alpha from this alloy, and then 50%, which is liquid. but that liquid has the composition of the eutectic. So we know that this 50 weight percent is going to go to the eutectic mixture. And so that's what we see below. So at the eutectic temperature, the remaining liquid at that composition turns into the eutectic solid. So that's what we see here. And if we do the lever rule just below, and we use the compositions of alpha and beta, this will give us the overall amounts of alpha and beta for this alloy. So we'll have 73% alpha in this alloy and 27% beta in this alloy. So we can do a lot of different calculations here to determine the different amounts of these phases and microconstituents that we have.